hallo, ich bin Henrik. Ihr habt schon gehört. Ich switch gleich zu Englisch. Der Grund ist, der ganze Research, das Denken, Schreiben darüber passiert in Englisch. Deswegen kann ich auch direkt auf Englisch darüber sprechen. Also vereinbart machen wir jetzt so. Okay, fangen wir an. Hi, as I said, my name is Henrik. I'm a designer and I work as a researcher at the Fraunhofer Institute for Optronics System Technology and Image Exploitation in Karlsruhe. As you can see from the slide, my talk is about explainable AI and how it must be shaped by UX to later work in healthcare. So what I'm giving you is a design research perspective, and the technical concepts are simplified. It is still complex as many different concepts come together here. But fear you not, I try to make it as straightforward as possible. So I'd like to begin with the promise. What you will get from this talk are three things. First, I will give a quick overview of healthcare UX and why it is somewhat special as a field. Second, I will lay out what explainable AI is and why it must be designed in a human-centered way. And last but not least, I will give you an example of what that actually means in practice and in the form of scientific research and experiments. So this is somewhat a densely packed talk, but I hope at the end you will find information and inspiration about these two fascinating topics. Okay, healthcare UX, what do I mean by that? As healthcare becomes more and more digital, clinicians have to deal more and more with data, and they do that through interfaces, of course. AI systems will first and foremost enter the healthcare domain as decision support. That is also the kind of systems that we are researching and dealing with at the Fraunhofer IOSB. If designed well, they will be an invaluable tool as many healthcare use cases become data problems. So two quick examples for this. For example, procedures like genome sequencing and other data-intensive diagnostic tools produce huge amount of data that only ML can process and make sense of eventually. The same goes for the ever-growing amount of relevant literature, which AI can help to sort and to make accessible for clinicians. Hence the IBM Watson system that is portrayed here. So this sounds as if all is working and super cool, right? Unfortunately not, and I have to be a little bit of a party crasher here because doctors hate their computers. And I believe they have very much reason to do so, and I will show you this now. Emergency department physicians spend 44% of their time entering data into electronic health records, clicking up to 4,000 times during a 10-hour shift. So you can see from this field report that the big issues in healthcare IT are usability and interoperability. And it is far from being solved. And now let's throw AI and what I will talk about XAI on top. Sounds a bit daunting, but let me be clear about this. At the end, useful and usable AI will make healthcare better. I believe that all our efforts in UX should be aimed at reducing screen time and increasing doctor-to-patient conversation time. This is like the big goal. So one design challenge that we're interested in is to find design patterns for XAI in healthcare IT. And we work on a clear premise here. The data subject shall have the right not to be subject to a decision based solely on automated processing, says the GDPR Article 2020, which means, in other words, machine learning will only work if it comes with usable explanations. This means that decisions on diagnosis and therapy must be taken by human physicians, period. That said, we should provide them with the best possible technology to assist professionals with making more informed decisions in the future. So let me unpack this notion for you. We start at the very beginning with what is a good explanation? Well, you can think of an explanation as the answer to a why question, as simple as that. By their very nature, explanations are interactive. In fact, they are conversations. And they are conversations about aligning mental models. The mental model of the explainer and the mental model of the explanee. So explaining requires some form of common ground and a common language. Now, the problem is, and this is really unfortunate, that machines don't speak human as of now. And explainable AI is the tool that shall mitigate this. So how might we design XAI interfaces to support mental model alignment? To answer this question, we, of course, must first understand what AI is. A little disclaimer, this slide will take a little longer, but it's somewhat important. It is the foundation. So, but we've heard some of this before, so I can also be a bit briefer here. Machine learning, or ML, is a set of computational methods used to make predictions based on data. And interpretable or explainable machine learning refers to methods and models that make the behavior and predictions of ML systems understandable to humans. So put in a nutshell, we as non-AI people may understand it as follows. So AI is the overall term, and ML is a subcategory of AI. It is a set of methods that computers use to make predictions from data, and that means from the past. Deep learning is another subcategory, and it's called deep because it has many computational layers. So we heard about this before. However, these mostly mathematic, algorithmic, or statistical processes are super complex, and it's often not possible to understand how the machine arrived at a prediction. But as we see before, this is crucial. So in that sense, ML systems are often black boxes, which is kind of unfortunate if you have to explain their behavior. So this is where Explainable Artificial Intelligence, or XAI, comes into play. So I'd like to think of XAI as a tool to open the black box. It shall provide explanations for machine behavior. Sadly, it is another very complex piece of technology used to explain already complex pieces of technology. These explanations are communicated to users through interfaces, which again tend to be very complex. So as of today, AI explanations certainly do not speak the language of non-technical users. They're very specific thing that has to be conveyed to non-AI people. So this fundamentally is an engineering problem and a design problem. To dive a little bit deeper, let me give you one example of an XAI model. So LIME is a relevant XAI model that is widely referred to, and it stands for Local Interpretable Model Agnostic Explanations. It's a thing that we use as a research object in our research. Model agnostic means that it can be used on different ML models. And what LIME does, and again, this is super simplified as I'm not an ML guy, but designer, what LIME does is for this network, throw in random values for a given prediction problem, for example, and observe the outcome. And thus it can make a highly probable prediction which attributes of the data set that went into it did contribute to the ML system's prediction and to what extent. The thing is that there's currently very little research on the effects that the way we present these explanations as interfaces has on a user's decision-making. But these effects are crucial in high-risk, high-stakes decision-making, such as healthcare. So let's have a look at the types of decisions we might encounter in healthcare and the type of effects that may rise from cognitive biases that we are interested in. So first, assessing probabilities. We know from psychology research that people are generally bad with probabilities, and unfortunately, physicians are no exception. So there are classic experiments where, for example, physicians were asked to estimate the probability that, for example, a woman has breast cancer, where the true probability was 7.8%. However, in this experiment, the researchers report that 95% of doctors estimated this probability to be between greater than 75%, because applying things like Bayes' theorem in your mind is super hard. And therefore, we need to support these kind of decisions. Also, it might not be the best idea then to communicate explanations only in terms of probabilities and accuracy scores. The second effect that's worth mentioning is framing. So another experiment, two groups were given also a medical problem and with two treatment options, and one was framed as a survival rate and the other as mortality rates. So the researchers found that the positive framing leads to more risk-averse choices, while the negative framing increases risk-seeking decisions. These are just two examples, and you may ask yourself, why does it matter for interaction design? Well, our notion is that visuals and interfaces do frame too, and this very fact has not thoroughly been researched in the context of XAI and UX. Okay, let's catch some breath. The takeaway so far. Our goal in our research is to understand how to design decision support systems that eventually speak the language of the user, and we want to take into account their cognitive biases. To this end, we need to ground design decisions in evidence. We need interface design that can educate the users to make more informed decisions based on AI recommendation. This concept is referred to as trust calibration. We need trust calibration through design because there are two major biases that come into play in these kind of scenarios. That is user overconfidence and automation bias. In other words, there are cases of undertrust or user overconfidence where trust in the machine must be promoted. That is when the advice tends to be accurate and reliable. And there's the opposite, overtrust or automation bias. And we need to somehow calibrate the interfaces as to take account of these effects. Therefore, we have to design ultimately for trust calibration and comprehension. And this is what our research is about. And to give you an example where HCI is with that right now, I have two examples of interfaces for explainability models. And just by looking at these, you can see or gauge the kind of complexity we are dealing with. So just to make this one bigger, this is like an example from a clinical decision support system, also in a research state. And what's interesting here is the upper right-hand corner with these bar charts, so to say, that give a prediction. And this is the way it's mostly done. But as I said, it's not thoroughly been researched what effect this kind of visualization has. So you could always argue, why shouldn't I pick like the most likely option when being overwhelmed with such complex information? So what we have to do when we want to research these kind of things and to design research is to break it down, even more so because we are facing a couple of really hard problems when doing research on this subject. The most pressing challenges stem from the very nature of intelligent systems, and that is that they are learning systems. And as such, they evolve and change over time, which means that at the end, one size fits all design patterns will likely not work. And the overall question is, how do you actually rapid prototype this stuff to rapidly test it? We meet this challenge with dynamic frameworks, exploring dynamic research frameworks, exploring design spaces. I will come to this later. And second, research in expert domains is difficult because the availability of experts is limited, which means we have to deal with small sample sizes, which usually is a problem. And also the research in healthcare with sensitive health data is ethically and legally problematic and also takes time. Therefore, in this case, we'll rely on a so-called human-grounded approach. And this means that we devise experiments with proxy tasks and real humans to gain insight and then transfer the findings into the expert domain we actually design for. So to say, proxy tasks from a different domain are our prototyping material for this kind of AI scenarios. And this is an example of how we actually do it or did it in the last year. So this are the so-called co-design experiments. Here, we first pick a task. In this case, we are trying to understand how people perceive and interpret the type of explanations as they are currently produced by XAI models. So we came up with this proxy task for making estimations based on a data set and AI advice. We picked the Lime model as it is relevant to medical AI. The task is about estimating the grade of a student based on a list of attributes like class failures, family relationship, and so on. This is a general proxy for making an estimate based on a given set of facts, as you would also encounter in this medical decision problems. You, as the participant, are given the values for a student and make a first estimation. At the same time, an ML system, a random forest, does the same and comes up with an estimation of its own, the advice. The advice and an explanation is presented to the human decision maker. The explanation is a diagram, as you can see here, and it depicts which attribute contributed to the advice and how much. So with that new information, you have the chance to make a second estimation. And thus, we as the researchers can observe and measure if and how much you adhere to this ML advice. The measurement is called weight of advice, and we use it as an indicator for the degree of trust into the system. So this is like the basis for the next step in the research. And this is where it really gets interesting, because this is part of a bigger study design, where also the whole notion of human-centeredness comes into play. So it has two steps depicted by the blue and pink swimming lanes at the bottom. First, in the blue lane, we work with fewer people in participatory design workshops. So we give them the task, and after being primed with the task, we then ask them to sketch better designs for the visualization of the explanation. By this, we kind of want to learn more and understand how people perceive it by really engaging in design activities with them. The next step is to synthesize the results and aggregate them in new user-generated design concepts, if you will. And we take these concepts as input for the second phase, and which is depicted by the pink swimming lane, and that is online user studies with many, many people and large sample sizes. And in basically the same experimental setup, we can then observe how the explanation design perform in terms of trust calibration and comprehension. So thus we collect evidence, and this evidence will serve as a grounding for future design decisions and shall inform other researchers in this field. And no worries, I will come to the end shortly. So this is just an example from the workshops, the kind of visualizations or different design solutions users create in these workshops. For example, here you see that one common feature was to change the visualization from bar charts or tornado diagram to pie charts. So we took some of these concepts and tested them on a massive scale. And eventually what we do is to visualize the results as so-called design spaces. That is, we take what we learn and we kind of give you an overview of what design solutions work best for what use cases. So you can see we have a measurement for the trust calibration and for the complexity. And then depending on your explainability problem, we can make recommendations which design solutions would work best. For example, we found out that the pie chart visualization has a rather trust promoting effect. So coming to the end, 3 things that you can remember and take home with you. First, we found that different visualizations have significantly different effects on the weight of advice. So this may sound trivial, but it has not been researched thoroughly in this specific context. So we follow that trust calibration can indeed be achieved through design interventions, and we will continue to research how exactly. Second, designing explanatory interfaces is highly task specific. This means there's a legitimate need for dynamic research and development of dynamic research frameworks such as ours. And last, design spaces are eventually the research artifact that we hope is able to communicate this evidence for you practitioners for future design decisions. And currently we are working on making this method accessible and applying it in healthcare use cases. Now, with that new insight, what is left to do is to take this knowledge and put it to use so that doctors won't have to hate their computers in the future anymore. And thank you very much. And I'm happy to take questions and get in touch. And we can also do the questions in German or in English. Both will work for me. Thank you. Danke.